Good afternoon, everyone. Welcome to Quarks to Quasars, a series of talks on physics and astronomy presented by Horizon IIT Madras. Our speaker today, Professor Debarati Chatterjee, is a theoretical astrophysicist working at the Inter-University Center for Astronomy and Astrophysics at Pune. Professor Debarati has made numerous contributions to various fields of physics and won several accolades along the way. Having received the Alexander von Humboldt Fellowship and the Department of Atomic Energy Gold Medal, Professor Debarati has always been an inspiration for women in STEM, and very rightly so. Apart from her obvious love for all things physics, she continues to break stereotypes associated with scientists in general, and more specifically women in STEM, as an artist, a trained Bharatanatyam dancer, and an adventure-seeking rock climber. Honestly speaking, ma'am, I'm confused as to which aspect of your personality is more inspiring. It's an honor to have you with us. Over to you now.
Thank you so much for this lovely introduction. It's my immense pleasure to be associated with this fantastic series organized by Horizon Club of IIT Madras. Thank you for finding me. Today it's a Sunday, so I don't want to talk about equations and very heavy stuff. So let's discuss what's going on in the frontiers of neutron star physics. And I will try to give you a brief glimpse into this exciting world, which is very complex and interdisciplinary. So it's very difficult to present everything within an hour. But I hope this will give you the appetite for finding out more about this exciting field. So let me talk about neutron stars today. So as soon as we head out of the city limits, away from the pollution, the light pollution and everything, so we see this sky full of amazing stars. And what is even more fantastic is that these visible stars form only a very small fraction of this universe. So, and the reason is this, that our eyes are perceptible to only a small fraction of the entire electromagnetic spectrum. And this is the only confined to the visible part. Whereas it is possible now to scan this entire sky in many frequencies, much like we do in medical imaging these days. So like we scan the entire body from gamma rays to X-rays and up to infrared and radio waves. In the same way, now with the advance of technologies, it is possible to scan the entire sky from gamma rays to optical, radio and X-rays. And this is possible with the large array of space-based and ground-based telescopes that we have today. Of the many fantastic objects that are visible in this multi-wavelength universe, let me draw your attraction to this one particular object. So you can see on the right this object, which is visible in different frequencies. And you see a supernova remnant, which is basically a dust cloud. But at X-ray frequencies, you see this object lying at the center. And this object is actually a compact object with a beam of radiation. So let's find out more about what this object is. For this, we have to look at the stellar life cycle. So stars typically keep burning their fuel, the fuel in the interior. Let me go back to this. So, and the pressure balances the gravitational attraction, and this goes on until iron is accumulated in the center. So from hydrogen burning, let me go back to this animation again. So hydrogen, for example, in the sun, is burnt to produce helium, and thus the thermal pressure supports the star against gravitational collapse. And from hydrogen, we can form carbon, oxygen, neon, and until iron is formed at the center of this the star. But iron, as we know from nuclear physics, is one of the most bound elements, and burning iron further will not produce energy. So what happens is that in this stage, the collapse, the burning of the fuel does not produce more energy, and there is nothing to support the star against gravitational collapse. So what happens is that we see this. Let's see this again. So this, the outer layers of the star collapse towards the center. There is a rebound when the densities reach nuclear densities. Then there is a shock wave which bursts these layers out into interstellar space, leaving behind a compact object. And this is called a neutron star. Neutron stars are also called Neutron stars are also called pulsars because they emit pulses of radiation. So as you can see that when these stars rotate, and they rotate very rapidly, they emit electromagnetic radiation along their poles. And this sweeps the Earth like a lighthouse, and this is why we perceive these pulses, and these are extremely periodic pulses. So these objects, or neutron stars, are also called pulsars. So with the help of these multi-wavelength astronomical telescopes, we are able now to observe a large number of phenomena associated with neutron stars, from which we can actually derive several observables. For example, we know about their spin period, we can deduce their masses, particularly from relativistic binaries of neutron stars. Precision in neutron stars can also provide us with its moment of inertia, and this is again a product of the mass times the radius squared. The radius can separately be determined from different observations, particularly thermal ones, associated with hotspots. But there has been a recent advancement in this regime, and that is the launch of the NICER mission, which is actually the Neutron Star Interior Composition Explorer. And this is supposed to give us accurate estimates of the radius up to 5%. There are also, for example, this X-ray spectra over here. And from these spectral lines, we can also determine the gravitational redshift, which also gives us the compactness or the ratio of the mass to the radius of the star. Neutron stars also show a variety of extremely energetic phenomena like flares and outbursts, and these indicate that they have extremely large magnetic fields. So here let's look at what knowledge we have accumulated about neutron stars. So basically we know that these are compact objects which are formed at the end point of evolution of massive stars that end in the supernova explosion that I showed you before. And the observables that I talked about can be summarized in this fact sheet. So masses of neutron stars are about 1 to 2 times that of the sun, or solar mass. The radius, however, is extremely small, so it's only around 10 kilometers. So basically from this you can do a back of the envelope calculation and see that the densities in the center of neutron stars can shoot up to 10 times that what we see in nuclear experiments. So 10 times that of saturation nuclear density, which means that neutron stars are actually the densest form of matter in the universe. Apart from these facts, neutron stars are also extremely cold compared to the energies of particles that are the constituents of these kind of objects, and there could even be superfluidity in the interior. Fields are again extremely high. For normal pulsars, you can already guess that normal neutron stars, when they collapse because of magnetic flux conservation, the magnetic fields blow up to about 10 to the 12 Gauss. But there are even a class of neutron stars called magnetars, which have been discovered recently. And it has been found that these have surface fields as high as 10 to the 15 Gauss. And some energetic calculations, which is also called virial theorem, they indicate that in the center of such objects, magnetic fields could be as high as 10 to the 18 Gauss. So this is by far the most magnetic object in the universe that you can think of. So of course, it is extremely challenging to be able to model these kind of things or to understand the physics that's going on inside these objects, because they are so far away from our current understanding that we can probe with experiments. So in order to understand or have an idea about what kind of matter we can have at such extreme densities that exist in the center of neutron stars, let us delve into the fundamental physics, the knowledge that we have accumulated from nuclear experiments, from nuclear theory, from particle physics, and so on. So the standard model that we have existing right now tells us that the matter that we see around us is composed of atoms. These are again formed of a compact nucleus in the center and an electron wave or orbit, or electrons orbiting around this central dense nucleus. This nucleus in turn is made up of protons and neutrons, and if you go further deeper, then protons and neutrons are again made up of fundamental particles called quarks. So there are two main classes of fundamental building blocks of matter, which is leptons and quarks. So electrons are one example of leptons. Quarks are thought to be of 6 major types. And the standard model of particle interaction tells us that the protons and neutrons, which are called baryons, they are actually formed of 3 quarks, which are confined to form a baryon. And on the other hand, pions and particles like that, they are mesons, and they are formed out of a quark-antiquark pair. So in total, these classes of objects are called hadrons. And there are different forces that we know about as well. We know about the electromagnetic force, the weak force, the strong force, and the gravitational force. And these are again mediated by force carriers like the photon, the gluon, and the W and Z particles. So we know quite a lot about electromagnetic theory, and actually the theory of strong interactions has been inspired a lot by quantum electrodynamics. So that's why it's called quantum chromodynamics, in analogy with quantum electrodynamics. And there are subtle differences, of course, if you go into the details, but very generally we can say that just as in quantum electrodynamics, we have the photon carrying as the force carrier. In the case of strong interactions, it is the gluon. And there is one major difference in the two types of interactions, because if you see this figure at the bottom, you can see that the coupling constant in the quantum electrodynamics is the fine structure constant, and basically this coupling, the alpha coupling, it decreases if you go to lower energies, right? And on the other hand, for QCD, this is the other way around. So this is one of the remarkable features of quantum chromodynamics, is that as you go from lower energy to high energy, lower energy is where these quarks are confined into hadrons. And as you go to higher energies, this is something called asymptotic freedom, where the alpha coupling becomes extremely small, and the particles, the underlying quarks, are free in nature. So let's see what what kind of information about strong interactions we get from terrestrial experiments. So from nuclear experiments, we get a lot of information about nuclei and about nuclear matter. So for example, we know about the binding energy of nuclei as a function of its mass number. And this I already mentioned when I said that this is one of the main features which controls the evolution of star, right? So this is what I just talked about previously. So hydrogen burning into helium, and then lithium being formed, nitrogen until iron is formed, and this has the maximum binding energy. So this is one. So binding energy per nucleon versus mass number. This is one of the very important quantities that we obtain from nuclear experiments. The other thing is that there is a difference between nuclei and neutron star matter, or basically nuclear matter. And it is, if you see in a very colloquial term, you can say that it's the difference between, say, a bottle of water and the ocean. Because as soon as you have a confined nucleus, you have surface effects, you have surface properties which need to be taken into account. So nuclear matter is something like this ocean of nucleons and interactions among them. The other thing that nuclear experiments tell us about is the nature of the strong nuclear force. So we know that nuclear interaction has a very strong repulsive nature at close distances, whereas it has an attractive interaction at longer distances. So these are very fundamental properties which we take into account when we construct nuclear models and when we also construct neutron star models. The other thing that nuclear experiments tell us is the differences between the behavior of neutrons and protons. So there are certain nuclear properties in which are absolutely blind or independent of whether it's a neutron or a proton, which means it is isoscalar with respect to asymmetry properties. Whereas there are certain properties which depend whether it is a proton or a neutron, or they are isovector with respect to neutron-proton asymmetry. So there are experiments like the electron dipole polarizability, the giant dipole resonances, which give us information about this kind of asymmetry in neutrons and protons. So this is actually extremely interesting for neutron stars, because neutron stars, they are composed primarily of neutrons. And this is one of the fundamental differences with nuclear experiments, because nuclear experiments have the same number of neutrons and protons in most cases. There are, however, some experiments, as you can see on the figure on the right, like isol trap experiments that I have worked in a laboratory for particle physics in France, and they are associated with this kind of experiments. And what they do in these experiments is that they go far away from the beta stability line, which is basically the line you can see. These are the black lines here are the stable lines, and these experiments actually probe nuclei which are far away, and they are far away from stability, and they are extremely neutron rich. So these are actually of very interesting for studies in neutron star physics. What about going to further energetic experiments? So you know that in order to go deeper from atomic levels to nuclear levels to even further, we need to go to higher and higher energies, right? So heavy ion collision experiments, which go on in particle accelerators, such as CERN in Europe. There is also the GSI, which is a particle accelerator in Germany. There is the Ganil particle accelerator in France, and so on. And also in the US, there are a large number of heavy ion collision experiments. So what these tell us is about even denser matter than we can probe with only nuclear experiments. So what happens in these particle accelerators is that beams of nuclei are made to collide, and these produce a large number of particles which are then tracked down and identified thanks to the masses and their charges. And so basically this reproduces the evolution in the universe, if you like, because there is the explosion, and there is a quark gluon plasma which forms in the interior, and then as this plasma cools down and thermalizes, then there are the production of hadrons and so on. So this, if you like, this probes the kind of matter you would expect in the early universe. Also, not only that, as you can see in these figure summaries, there are a large number of experiments that go on in these kind of particle accelerators. Hypernuclei are formed, and hypernuclei are extremely important for neutron stars, and I will tell you soon why. So these hypernuclei are basically, if you like, they are like a normal nucleus where you can replace one or some of the quarks by from normal quarks to strange quarks. So in that case, you will obtain heavier hyperons, like in this octet, the baryon octet from the standard model of particle physics. This tells us that neutrons and protons are the lightest baryons, and then you get lambda particles, sigma particles, and so on. And these also have strange quarks in their interior. So basically, if these hypernuclei are also probed in heavy ion collision experiments. Other than that, K mesons, so these are kaons or K mesons, and these are also produced. So all these kind of strangeness containing matter is also seen for a very brief amount of time in particle accelerators. And the reason is that these particles can only be formed at extremely high energies because of their large masses. So as you can see in this world map, there is a cluster of different experiments, and these experiments are hypernuclear experiments which are probing the properties of these kind of hypernuclei. There is also another very interesting experiment coming up soon, and this is called the CBM, or compressed baryonic matter experiment. This is going to be set up at the FAIR facility, the Facility for Antiproton and Ion Research in GSI in Germany. And what is interesting is that this is going to probe dense matter at about 4 or 5 times that of saturation density. So this is one of the most dense kinds of matter that we can probe through terrestrial experiments. Now, what I'm going to try to convince you is that neutron stars actually give us a lot of information which is not possible to obtain only through building of large accelerators or through terrestrial experiments. And the reason is clear from this phase diagram of quantum chromodynamics. So just like water, ice, and vapor, you can construct a phase diagram of QCD in terms of its density on the x-axis and temperature on the y-axis. So nuclei, or the nuclear experiments that I talked about, these lie at around saturation density. So this density scale here is normalized to the saturation density of nuclear matter. So nuclear experiments can only probe up to saturation density. The heavy ion experiments that I talked about, these probe finite temperature and finite density matter. So these lie in an intermediate range of the density temperature curve. On the other hand, there are also theoretical advancements in the meantime that tell us a lot about the behavior of QCD at extreme limits. And one of them is the lattice QCD, which is basically solving for QCD on a lattice. And these require like supercomputers in order to solve for the kind of properties that we want to study. And so, like I told you, so heavy ion collisions, lattice QCD, they probe the high temperature, low density regime of this phase diagram. On the other hand, compact stars actually lie in a complementary region of the phase diagram. And so this is that of high density, low temperature regime. And as you can see, there is also another axis of this figure, which is that of neutron-proton asymmetry. And compact stars are, again, systems which differ from heavy ion collisions and nuclear experiments with regard to the neutron-proton asymmetry, because they have way more neutrons than they have protons in their interior. Now, please don't ask me what happens when you go to even higher densities, because there are lots of very complicated models which take into account the transition from hadrons to quarks. And also there are superconducting phases that can appear by virtue of the gaps that appear in this kind of calculations. And so there is a zoo of models out here which suggest what can happen at these large densities, but there is still a lot of uncertainty. So let's say compact stars can help us to understand the behavior of QCD far away from our knowledge of nuclear experiments and heavy ion collision. So with all the information that I already gave you, we can try to construct now the interior of the neutron star. So as you go from the surface to the interior, neutron stars span a wide range of densities, right? From nuclear densities to several times that of the saturation density in the interior. So at the surface, you find nuclei, like iron nuclei, and as the density increases, the nuclei become more and more neutron-rich. So this part is called the outer crust, where you have clusters of nuclei embedded in a sea of electrons. So as the neutrons get more and more neutron-rich at a particular point, the neutrons start to drip out of the nuclei, and this is called the neutron drip density. Beyond this density, the region is called the inner crust. Now you can see in this inset that as the density increases, these clusters of nuclei get more and more deformed because of the high densities, and they go through a very strange kind of phases, deformations, and they are funnily named after a lot of different pasta structures because they look like that. They are also called pasta phases. So they look like spaghetti and lasagna and so on until they finally dissolve to form a uniform a sea of neutrons, protons, and electrons. And why are there protons and electrons? This is because of chemical equilibrium and charge neutrality. What happens when you go further into the center is still a very big question. This is because this is way beyond the limit that we have information about from terrestrial experiments and from the state-of-the-art calculations of dense matter. And it is thought that what happens in the interior in the inner core of neutron stars is that the densities become so large that the neutron, proton, the in-medium energies become larger than the threshold for appearance of these heavy baryons or the hyperons that I talked about earlier. So in that case, you can expect to have hyperons in the center of the neutron star. And in this case, because of the large densities, they will even form stable components of the neutron star interior. Not only this, the kaons that have been seen, that I just told you about in heavy ion collision experiments, these can also appear and be stable components of the neutron star. And what is most fascinating is that you can even have deconfined quark matter as stable components of the inner core. Now, what is the possibility that we can actually find signatures of this kind of matter in the astrophysical observables that we are observing with the telescopes that are at our disposal? To understand this, we define something called the equation of state. So the equation of state is basically the relationship between the pressure and the energy density of cold dense matter, as we have in neutron stars. And these equations of state actually help us to model the interior of neutron stars, and in order to calculate global variables that can be compared to these observable features. So, for example, equation of state is one of the inputs that go into the calculation of the hydrostatic equilibrium equations, or the Tolman-Oppenheimer-Volkoff equations. And these equations are basically telling us about the balance of gravity and pressure that sustain the neutron star. And on solving these TOV equations, what you get are the mass and radius of neutron stars. So basically the global observables of neutron stars. And so this is very fascinating, because the equation of state, let me tell you, so if you look at the bottom figure on the left, these are, the equation of state curves are very different if you have only nucleons in the inner core, or if you have these exotic forms of matter, which are hyperons, kaons, or deconfined quarks. So what we think is that if these strange forms of matter appear in the core, there are new degrees of freedom, and this will result in taking away some of the pressure from the consistent nucleons, constituent nucleons, and this will result in a softening of the equation of state. So, or basically lowering of the pressure density relationship. And on solving the TOV equations, we can also relate them to the mass and radius curves. And what we know now is that nucleons typically should have, or basically stiff equations of state should have a larger mass compared to those of softer equations of state. So let's now compare this with observations that we can that we get from the different observations from telescopes. So particularly for the case of relativistic neutron star binaries, which show post-Keplerian parameters, from which we can derive post-Keplerian parameters in addition to the regular Keplerian parameters, they help us to determine the masses of neutron stars. So on the right, you can see a kind of chart which summarizes the different neutron star masses that have been determined from these kind of observations. Most of them, until very recently, were clustered around a canonical value of around 1.4 times that of the Sun. And with such a mass measurement, if we compare them to the theoretical models, almost all the nuclear models that we had were able to satisfy this kind of limit. So this was quite a relaxed limit, and so basically the idea is that the maximum theoretical predicted mass should be able to explain the maximum observed mass. So in 2010, and this is when I was a postdoc in Heidelberg University in Germany, there came a couple of fantastic discoveries which said that neutron star masses as large as 2 solar masses have been found. And now these can put very stringent constraints on the models of neutron stars. So the picture, unfortunately, is not as simple as I have put in the cartoon here, but a much more complicated one. And the reason is that there are a vast number of theoretical models which satisfy some or the other nuclear matter or heavy ion collision experimental observables. And So at least this red curve, the line that you see from these two solar mass limit, are able to at least filter out some of the equations of state, but not all. There is also an indication that the chaos experiment in GSI, this is also a heavy ion collision experiment, that this experiment gave us the indication that the equation of state of matter around 2 to 3 times saturation density is actually very soft. So this is very much in contradiction to the kind of information we have from two solar mass neutron stars, because these tell us that the neutron star equation of state should be extremely stiff to be able to explain this kind of observation. So at this time, I worked on, again, some results which tell us that in order to be able to reconcile these two complementary information about from heavy ion collision experiments like chaos experiment at densities around 2 to 3 times that of saturation density, and heavy ion and equations of state from neutron stars, we should have a kind of stiffening in the middle, which is associated with some kind of phase transition. Recently, there has been some amazing discoveries of gravitational waves that have changed this entire picture, and the reason is that gravitational waves are unlike the other multi-wavelength astronomical observations. Gravitational waves can actually help us to probe directly into the interior composition of neutron stars. So already back in 1974, Hulse and Taylor, they had indirectly proved the existence of gravitational waves by monitoring the Hulse-Taylor pulsar. And as you can see from the animation on the right, any kind of binary neutron star, they orbit each other and they come closer and closer together. And in the process, they emit gravitational waves. And using Einstein's theory, or general relativity, Hulse and Taylor, they predicted the kind of trajectory the neutron stars should follow, and the observations exactly match these kind of general relativistic prediction. So for this observation, which was the first indirect observation of gravitational waves, Hulse and Taylor were awarded the Nobel Prize in 1991, if I'm correct. And so after that, after this, there were a lot of experimental efforts in order to observe directly the gravitational waves. So this I will come to soon. So let's look at why neutron stars can be very interesting gravitational wave sources. So one of the reasons is that gravitational wave sources must have some kind of deformation. They should have some kind of non-axisymmetric deformation which varies with time. So in neutron stars, how can we have this kind of deformation? So there are different phenomena and associated with neutron stars. For example, there is something called glitches in neutron stars. So neutron stars basically are rapidly rotating and spinning down slowly by magnetic braking. Because they have strong magnetic fields, the magnetic braking allows it to slowly spin down or reduce its rotational velocity. There are certain points in this in certain neutron stars. There have been observations where there are sudden jumps in these very periodic, very monotonic decrease in the rotation frequencies. So this kind of abrupt increase in rotation frequencies are called glitches. So these glitches could be one such source of deformation, which is abrupt and produces gravitational waves. There are also kind of deformations which are called mountains on a neutron star. This is actually a funny term because mountains, it's not as we think of mountains like the Everest on Earth. Mountains on neutron stars are actually a few centimeters high at most because of the crushing gravity. But these bumps on its surface can basically also produce time-varying deformations, which produce gravitational waves. Again, I talked about magnetars, so these are extremely magnetized neutron stars, and these magnetars can have a lot of very energetic phenomena like flares and outbursts, and again these can produce gravitational waves. It is also thought that for magnetars we have magnetic fields as high as 10 to the 15 Gauss, and this can actually lead to a deformation or elongation of the surface of neutron star. From its spherical shape, it goes into an elongated shape, spheroidal or even a toroidal configuration. So this can lead to gravitational waves as well. We also know from fluid experiments on Earth that there are a number of different kinds of radial and non-radial pulsation modes. And these have been also extremely interesting in the case of stars or even, for example, the sun. Fluid perturbations are classified into many different modes, and these modes are named after the restoring force that helps to bring it back to equilibrium. So there are the fundamental F modes, which are the fundamental pressure modes. There are also the pressure P modes, the gravitational G modes, which are restored by buoyancy. There are the rotational R modes, and so on. In addition to these fluid perturbations, neutron stars also show a peculiar space-time oscillation mode called W mode. So I have been particularly interested to work on several of these oscillation modes, and it is fascinating because not only does it tell you about the interior composition of neutron stars, but also about the kind of interactions among these fluid modes itself. This is a very dynamic field, which is very evolving, particularly right now. I have worked a lot with R modes, so I'm just going to briefly tell you about what R modes are. So R modes are rotational modes which are restored by the Coriolis force. And the Coriolis force, you know, is also something that we know here on Earth and is responsible for many of the storms that you experience. So these R modes are modes which become unstable due to a mechanism called the Chandrasekhar-Friedman-Schutz mechanism, which is basically taking away energy by emission of gravitational waves. And this mode is has a different nature if you see it from a co-rotating frame or from an inertial frame. So while this rotational mode the frequencies of this mode are positive with respect to the inertial frame, they are actually negative with respect to the co-rotating frame. And the gravitational wave taking away energy from the system helps it to have a runaway kind of process, and this becomes unstable and results in a copious emission of gravitational waves. So all neutron stars or all rotating stars actually are unstable to R modes. And this kind of process is actually extremely interesting because it plays a major role in controlling the rotational frequencies of the stars. So for example, imagine a newly born, hot, rapidly rotating neutron star. So this, as you can see here, enters a region in the relation between the angular frequency and temperature. And this window, also called the instability window, is basically defined by this tug of war between gravitational wave instability and the viscosity in the medium. So viscosity tries to stabilize this kind of R mode. And so when a neutron star is rapidly rotating, newly born, it enters this window at a certain point, and this is where the neutron star R modes become unstable. So this the mode takes away so gravitational waves are emitted profusely from this kind of spin down, and so neutron stars now reach the other end of the instability window, where viscosity again helps to kill this kind of instability. So this instability, now this window, depends on what kind of matter you have in the interior of neutron stars. If you have only nucleons, the nucleons among each other will have certain weak processes, and hyperons, on the other hand, they will have a different kind of weak process associated with them. And these are, again, these have a different function of frequency and temperature, and define the two boundaries of this instability window. So basically, observation of gravitational waves from such a mode, as well as its rotation frequency, is going to give us information about the interior composition of neutron star. So this is something that I worked on during my PhD. And so following the indirect detection of gravitational wave by Hulse and Taylor, there was a massive effort all around the globe to build detectors. And these detectors are actually, they are basically L-shaped, and they are kilometers long. So each length, the length of each arm of the detector is something like 4 kilometers. And you can see in the picture on top the two LIGO sites at Hanford and Livingston, and the Virgo site at the border of Italy and France. And the reason why these are built like this are because they follow the principle of interferometry. And so there is a beam splitter which splits the beam onto two different mirrors, and any kind of non-axis symmetric motion which is given by a perturbation, the gravitational wave passing through this interferometer, is going to change the relative length in the two arms and change the interference fringes. So this is, of course, I mean, this is an extremely simplified picture. If you actually go into the details, you will see how difficult it is to isolate a gravitational wave signal from all the noise that we have, seismic noise and thermal noise, etc., around us. And so these gravitational waves are actually extremely feeble. So the LIGO mission earlier, so this was able only to detect, so this was sensitive only to up to 10 to the minus 21 or 10 to the minus 22, around 100 hertz frequency. And this was already an extremely a technological marvel, let's say an engineering marvel, to be able to have a target sensitivity which can detect an amplitude of 10 to the minus 22. This is something that this I found funny, that many of my colleagues have been working over past 10 years and with the LIGO collaboration, and it was very disappointing for them, because for 10 years they had been working with the best of technologies, and even then they were not able to detect anything. And they were only cutting cakes every time they reached their design sensitivity. But then came advanced LIGO, which had implemented even better technologies, and it had now sensitivities which went down to about 10 to the minus 23, 10 to the minus 24. So bang came the fantastic announcement on 14th of September 2015 of the first direct detection of gravitational waves from binary black holes. So if you noticed, tomorrow is the 5th anniversary of this event. So keep an eye on the LIGO India page. A lot of exciting events are coming up to commemorate this fantastic event. So this was the first time that gravitational waves were detected from compact binary merger. And for this, the Nobel Prize went to Barry Barish, to Anthony Hewish, and to Kip Thorne for this fantastic discovery, and for proving that, yes, we are capable of actually detecting gravitational waves from compact stars. So after this discovery, a large number of binary compact stars started to be discovered in gravitational wave universe, and there came suddenly a very different kind of signal from a binary merger, which was way longer. So all the other observations were a few seconds. However, this one was about 100 seconds, and so the gravitational wave scientists, they sat up and took notice, and what happened was they started to send messages to their electromagnetic counterparts and try to focus all their telescopes towards this event. And this was called the gravitational wave 170817 after its discovery date, and this was an event in the galaxy NGC 4993. So this was one of the most remarkable events that has happened in the neutron star physics community, because one particular event has never given so much information about so many models and so many theories and hypotheses of neutron stars that were at once simultaneously confirmed. So the reason is that the same event, this merger, was observed throughout the electromagnetic spectrum. Almost in every frequency band, this merger could be followed up to the coalescence. And so let me show you the animation. So here are the neutron stars in this binary merger, which spiral around each other. Finally, they combine and give off the radiation in different multiple frequencies. So the gamma ray component corresponding to this event was picked up by Fermi detector and also by the integral detector. The VLA, on the other hand, detected the radio component of this binary merger. The Chandra telescope observed the same in X-rays, and these all of these observations actually they confirmed a lot of different models which are associated with a merger of neutron star. For example, until this event, it was not known whether short gamma ray bursts are associated with binary mergers of neutron stars. There were models, and these were finally confirmed by this observation of gamma rays by Fermi and integral. Also, the optical images told us that such an event is associated with what we call a kilonova. So this is something like a supernova, but with let's say 10% of the energy of a supernova. So all these different models were all confirmed by these multi-messenger astronomy. So this was a new era of astronomy started with this event. And also the X shooter on VLT saw this kilonova event, as you can see on this picture on the right. And what is even more fascinating, this is one of the most fascinating things that I have seen in my lifetime. So this was the X shooter also found spectra of elements and absorption bands which corresponded to the formation of some heavy elements during this binary merger. So if you look at the chart of the periodic table, and you see that there are different heavy elements which are formed in which were thought to be formed in merging neutron stars, and until this event it was not confirmed, but so the cesium and the tellurium that were detected in the spectra that I just showed you confirmed that indeed this kind of nucleosynthesis occurs in binary neutron star mergers. So this means that all these different elements, including gold, platinum, and silver, that of course which are extremely precious to us, were formed in the interior of neutron stars, and when neutron stars merge to form a compact stellar object. there are a lot more fascinating things about neutron star mergers. There is something called tidal deformability. So basically, when neutron stars are going around each other in the pre-merger phase, they tidally deform each other. This is because of the very strong gravitational attraction. So because of the strong gravity of the neutron stars. So if you see the animation at the bottom, you can see that these tidally deformed neutron stars are merging to form the compact post-merger remnant. And what is fascinating is that this tidal deformation actually is related to the compactness of the object. So how much it gets deformed is related to the compactness and also therefore to the composition of the neutron star. So this is the first time that we are delving into the interior of neutron stars with the help of gravitational waves. So if you see on the right, there are this is an older image which was put forward by the LIGO-Virgo collaboration some years ago, just after the discovery of this object. Now there have been some modifications to this figure, but in general we can say that this kind of study of the tidal deformability of the participating compact stars in the binary tell you something about its compactness. And now we have also a simultaneous effort by numerical relativity teams around the world who are doing fantastic simulations in order to understand this kind of object. And soon we hope to be able to crack this puzzle of whether we can actually have exotic matter in the interior of neutron stars. There was another gravitational wave event of compact neutron stars, a merger of compact neutron stars, and this happened on 25th of April 2019. This was a bit of a disappointment after the GW170817 because, the electromagnetic counterparts this time did not observe anything in addition to gravitational waves, but we had another discovery, and this is that this was the heaviest binary neutron star ever observed. And if you see this figure from LIGO-Virgo collaboration at the bottom, you can see that there are many neutron stars which have been discovered in the electromagnetic radiation, and these above are all the different black holes. So the purple ones are the ones which were discovered in electromagnetic radiation, and the blue ones are those discovered by virtue of their gravitational wave emission. And as you can see that there is a gap, and this is also something called a mass gap, which is thought to exist between these two classes of compact stars. However, this was the first time that this discovery actually led to the formation of a post-merger compact remnant which collapsed into a black hole right in the middle of this mass gap. So as you can see that neutron stars and gravitational wave observations, these are opening up a fantastic new universe. And so this is just the beginning. And as you can see, each observation is full of surprises. It's telling us more and more about what we did not know about compact stars. This is a very, very dynamic field. And look out for many more such discoveries. We have now a global array of detectors. In addition to the LIGO detectors in the US and Virgo in Europe, there is also the GEO detector in Germany. Recently, the CAGRA detector, the gravitational wave interferometer, has come into observation in Japan. And this is now the LIGO-Virgo CAGRA collaboration. Soon, LIGO India is supposed to join this band. So LIGO India is a planned gravitational wave mission, which plans to move one of the LIGO detectors to India, close to in Maharashtra, and this is actually fantastic because as you can see, most of these other detectors are actually in the same plane. And if LIGO India is least we should be able to have better sensitivity and better location of the gravitational wave events. There are also many other projects that have been proposed. There is the Einstein telescope coming up, which is supposed to have even better sensitivity than the Advanced LIGO. There is the Cosmic Explorer. There is also something called NEMO, which is coming up in Australia. So all these are proposed missions and work in progress. As you can see that the gravitational wave universe is just starting to open up, and neutron stars are going to tell us so much more about nuclear physics, which is unknown to us today. So thank you very much for your attention, and please feel free to ask me questions.
Thank you for the insightful talk, ma'am. The first question we have is the TOV equations come from general relativistic collapse and don't involve quantum mechanical corrections. So how are they trustable?
Okay. So the Tolman-Oppenheimer-Volkoff equations basically take into account the hydrostatic equilibrium of the neutron star, which is the balance between the pressure and which is for the case of neutron stars, it is a Fermi degeneracy pressure and the gravitational attraction. So if you like, quantum mechanics is involved in a different way here. So the Fermi degeneracy pressure comes from the fermions, which have, let's say they avoid each other, and this gives result to a pressure. This is called the Fermi degeneracy pressure. So this is definitely taken into account when we are talking about the Tolman-Oppenheimer-Volkoff equations for the case of neutron stars.
Thank you, ma'am. The next question is, can you comment on how we say that the mystery object of GW190814 is a neutron star and not a very low mass black hole?
Are you talking about this object or the other one?
No, not this one. So 190814.
Right. So yeah, I haven't included this in my talk because this is a very recent discovery, and also it is not confirmed whether it's a neutron star. So yeah, also this object that you're talking about falls somewhere in the mass gap, and this observation indicates that the remnant mass is around 2.6 solar masses. So this is very difficult to explain with even only nucleonic matter, because of course if you do not include nucleon-nucleon interactions, you cannot explain any of the neutron star masses. But again, you need to take into account realistic nucleon-nucleon interactions. So currently, all the different models, they are, even to the most extreme limit, they cannot explain a nucleon-nucleon interaction, which is as repulsive as to produce a neutron star, which is 2.6 solar masses. This was basically rule out all kinds of hyperons, all kinds of exotic matter in the interior, and probably only a very few models with extremely stiff equations of state would survive. On the other hand, being a black hole is also, it's a difficult explanation, because this would in that case be the lightest black hole that we have ever observed. So this is an open question, and yeah, do look out on the LIGO India blog pages, which will come up soon, and we are going to talk about this there as well.
Ma'am, the next question is, do all rotating stars radiate gravitational waves?
Sorry, do all rotating stars?
Do all rotating stars radiate gravitational waves?
Yes, so all rotating neutron stars, they are, like I mentioned, they are unstable with respect to the R-mode instability, but then this instability can again be balanced out by the viscous forces inside the star. And these forces are again dependent on the composition of the neutron star. So this is something that I have intensively worked on during my PhD and also later. And this is a very dynamic field. And also it is very difficult to take into account all the processes. So not only weak processes, but also there is superfluidity, magnetic field that can play a role in saturating the amplitude of these kind of unstable modes and so on. So let's say generically all rotating neutron stars are unstable to our modes and to emission of gravitational waves, but whether or at what point in their evolution they will become stable depends on these viscous forces inside the star.
Thank you, ma'am. The next question is, can a neutron star and a black hole form a binary system?
Yes, of course. And this is a very interesting question because this is something that gravitational wave scientists are frantically looking for. You can imagine, so this is basically like a clock going around a black hole. So it's going to tell us, because if we can observe the pulses from the neutron stars, we can also determine the effect that the black hole has on it. So these relativistic effects are going to tell us a lot about the neutron star and the black hole. So this is something that we are all looking forward to.
And what would the merger be like in that case? The outcome of said merger?
So all these compact mergers that I talked about, so be it a black hole merger or all the black hole neutron star or neutron star, eventually they all end up in, okay, let's not say they all end up in neutron star, but many of them end up as black holes. The reason is that when these massive objects collide, they form a post-merger remnant, which is also extremely massive. Now, depending on whether this mass can be sustained by the the constituents of the neutron star, will tell us about the stability of this object. So basically, if it is supermassive, if it is hypermassive, so depending on its the kind of matter you have in the neutron star, you can sustain a different post-merger remnant mass. And this is actually very interesting for us to study. This is something that I'm also working on in order to understand what kind of matter you have in the interior. So let's say most of the objects that we have observed until now, these post-merger remnants have been stable up to a certain time, and beyond this they have collapsed into a black hole. So either it could be a prompt black hole, which means that immediately after the merger it forms a black hole, or there could be a post-merger remnant which is stable or becomes unstable while it is cooling down and collapses to a black hole. So the post-merger remnant, the outcome will depend again on a number of things. It depends on the initial masses of the neutron stars or the compact objects in the binary, of the differences in the participating masses of the two objects, and so on.
Ma'am, the next question is, what is your opinion on supersymmetry?
I'm not sure if this is relevant to this topic.
Okay. Coming to the last question, do you have any advice for women looking to make a career in physics?
Advice? I would say like this Horizon Club is trying to ignite the passion of astronomy, of science, of physics in everyone. So definitely, I would say that physics in general, astrophysics, it's a difficult field. It's extremely competitive, not only for women, it's for everyone. And so anybody who is interested in this field has to be determined, has to be passionate about it. And I would say I'm trying to make my best efforts in order to inspire other women to come forward and try this extremely exciting field. If you have any further questions, please don't hesitate to contact me.
Thank you, ma'am. That was a very insightful talk. great to have you with us.
Thank you. Thank you for your invitation.